Hello. In this video, I want to look at the direct comparison test. So with the direct comparison test, we deal with two series. We have one that adds from 1 to infinity for the sequence an, and we have another one which takes the series summation from 1 to infinity, and then that would be the sequence bn. We have that the condition would be that an would have to be less than or equal to bn. And let's go ahead and make an strictly positive. And this is going to be for all n greater than or equal to big N. And we have two statements, basically, for the direct comparison test. We have that if bn converges, then an converges. Okay. But then we have that if an diverges, then bn diverges. Now note that that would require a certain order of the inequalities being satisfied, that is. So we just have to make sure that, that this is going to be okay, if you will. So let's say that, for instance, that we take a series, and let's say that that series is from n equals 1 to infinity, and suppose that this is going to be 1 divided by 2 to the n, but it's going to be plus 1 in the denominator. Now in either case, the things of which that we do know is that we are trying to show something about this sequence in either case. So either it converges or it diverges. Now, the thing of which that we might want to work with, for instance, is that let's go ahead and say that an is equal to 1 over 2 to the n plus 1. But then from here, let's say that we take bn, and we're going to say that this is going to be 1 over 2 to the n. Now the thing of which that we can explore with this is that, for instance, we know that in looking at the 1 over 2 to the n plus 1, that you more or less want to find a sequence of which that compares to it, that is. So usually we tend to just truncate the term and just say, okay, well, get rid of the 1 over 2 to the n. But the question, though, becomes, what do we know about 1 over 2 to the n? And when I rewrite it as so, like 1/2 raised to the n, I realize that basically that this particular series is geometric, but it's a converging geometric series. So we have that this is a converging geometric series. Now what that means, though, is that if this is a geometric converging series, that means that we would just need to show that these inequalities are true, that is. So notice how, like, for instance, we could look at 2 to the n, and for sure, that's going to be less than or equal to 2 to the n plus 1. Now, knowing that basically you have that proportionality can be obtained, we have that when we kind of flip this, we have that this becomes 1 over 2 to the n plus 1, and this is less than or equal to 1 over 2 to the n. Which in either case, notice that in this sense that this is going to be the sequence bn, and this right here is the sequence an, which technically would mean actually, is that not only did we satisfy the inequality, because we have it right here, that, the left-hand side is less than or equal to the right-hand side in this case, then we satisfied it. But notice that in this case, that is exactly what we wanted to show, right? That you have that since Bn is a converging geometric series, that would also imply that the series from 1 to infinity of 1 over 2 to the n plus 1 is also a converging series, that is. So that means that basically once that we've shown those two, is that we can say that the series of 1 over 2 to the n plus 1 it converges by the direct comparison test. Okay. And that's not that bad, really, when you think about it. Now, we also have that, for instance, like, let's say that we used the same principle, and let's say that, for instance, that we now look at perhaps, let's see, n equals 1 to infinity. And let's say that for this one, we could probably just look at n divided by, in this case, let's suppose that that's going to be n cubed plus n plus 1. Now here, it's not really too clear as to, what kind of comparison can we make. But I do know that an is n over n cubed plus n plus 1. So what would bn be? Bn would have to be basically some near approximation of that. So we can take n and divide it by n cubed, and this equals to 1 over n squared. So here, looking at it like this, I have that the series of 1 over n squared, well, basically we have that this is a converging p-series. Okay, so we have that this is a converging p-series, and that's due to the fact that p is equal to 2, which is greater than 1. Now, from there, though, what we could do is say that, for example, that we start with maybe, in this case, the let's see, because yeah, we want to be able to satisfy this inequality, right? So I think that it would probably be best that we go ahead and we just say, well, if I have that n cubed is less than or equal to, like, let's say less than or equal to, for sure, n cubed plus n plus 1. We can see that that definitely would be true, right? But then, if I was to say that, for instance, that we do the same thing with the proportionalities, and we just say that that's going to be plus n plus 1, and then that's going to be less than or equal to 1 over n cubed, then all that we need to do from here is just multiply by n on both sides. So we have that this would be multiplied by n on both sides, of which, in any case, what would we get? But we would get that essentially this gives us the n over n cubed plus n plus 1 is less than or equal to, well, n over n cubed, which is equal to 1 over n squared. So in this case, this gives us our an is less than bn, which means that we've satisfied that as well. Usually you might want to do that first, but I mean, I think that it's better to just identify what we have first, and then from there we can see like which of the conditions are we trying to satisfy, which in this case, 1 over n squared, it's a converging series, so we just have to show that the sequence an is less than, okay? Now, suppose that, we had something like, say, for example, a natural log. Okay, now usually you might think that, well, if I have a natural log, then maybe I need to use a integral test. So from here, you kind of have to do it the same way, where you have to think about, okay, well, what do we know about natural log of n? Well, natural log of n, for sure, is less than or equal to, let's say, like n. But in actuality, it's more like, less than for sure, because if you look at it on the graph, they are less than, okay? But here, what if I was to use the reciprocal? So if I use the reciprocal, then in that case, you're going to end up with 1 over n, and this is less than 1 over natural log of n. But this tells me that I have found the sequence of Bn, and this tells me that I have found the sequence of An. But what do we know about An for sure? Well, looking at, the 1 over the n, this is a divergent harmonic series. Okay? Now, due to the fact that basically that it did satisfy the inequalities for the divergence thereof, that would imply that, we basically have the conclusion that the series from n equals 1 to infinity of 1 over natural log of n, well, basically this diverges by the direct comparison test. Okay, now, in any case, for example, if you had looked at other sequences and series, it is possible that there may be some inconsistencies, which why I kind of consider the direct comparison in some cases not exactly the best method of testing for convergence and divergence thereof. Because, for example, if you were to look at the series from n equals, well, it would have to be 2, for example. Like, let's say that we start at 2 and this goes to infinity, and this is 1 over n squared minus 1. Now, for this one, I could probably say, for example, that definitely n squared minus 1 is less than or equal to, let's say, like n squared. But when we, well, let's say that we just get rid of this, right? Okay, so when we rearrange this, this is 1 over n squared, and this is less than 1 over n squared minus 1. But technically that's not what we're trying to show, right? Because this doesn't work. So we see that the direct comparison test, this doesn't work. So in any case, we can show that this converges using possibly maybe an integral test, or maybe looking at possibly the bounds of this, to show that it's a monotonic sequence or something like that. But yeah, it just doesn't work, right? So that means just apply another test, basically. It's kind of like an inconclusive, if you will. Well, similarly, if you have, for instance, n equals 1 to infinity, and this is 1 over the square root of n plus 1, well, for instance, we have that, for this one, that for sure the square root of n is less than basically the square root of n plus 1, and this would work for n greater than or equal to 1 per se. So if, for example, we do the the same thing where we have 1 over the square root of n plus 1, and this is less than 1 over the square root of n. This is not the same thing that we needed either, because for this one we needed the diverging part, because see how 1 over root n, it's a diverging series, 1 over root n, but it's not in the same conditions that it needs, because it should be the other way around technically. So this doesn't work either. So we have that this would be actually inconclusive. Now, what I would like to do is to kind of end with a direct comparison that is not really going to be as involved, for instance. So let's say, for example, that you have a nice series, and this is n equals 1 to infinity, and let's say that this is cosine of n divided by n squared. Now, For this, if you were to expand it, you would get cosine of 1 divided by 1 squared plus cosine of 2 divided by 2 squared, and so on. Now, for this one, you could probably just say, well, I know that for the absolute of cosine of n, that it's going to be always less than or equal to 1, for instance. So for this one, we have that essentially this is going to give me that if I have, the absolute of this, that we have that it's less than or equal to 1. And in either case, what we could probably do is just say, well, we have that cosine of n, and we divide both sides by n squared, is less than or equal to 1 over n squared. Now, in this case, this looks like it could be our bn, and this right here on the left-hand side of the inequality is our an. But what do we know about, for instance, the series of 1 over n squared? Well, basically we have that it's a converging p-series. So we have that that's a converging p-series, and in either case, we have that basically the inequality is satisfied because we have that bn converges. Then by that form of logic, that we can basically conclude that the series from n equals 1 to infinity, let me fix that, of cosine of n divided by n squared, that this converges by the direct comparison. Okay, so we have that this converges by the direct comparison. But, something that I'm wondering is that basically for this one, like what if you had, for instance, that this was the sine function, and in that case, that would imply that basically it'd be more or less the same process. So, if you want to, you could probably just try the series of sine of n divided by n squared and see, like if that goes from 1 to infinity, what would that series do? And, basically it would more or less be the same idea because the sign oscillates. And you would see that it goes from positive to negative, but it's not technically in its form the alternating series that is, though. So just be careful with this, and hope this helps.